Okay, let's take a look at these last couple problems that I had not done in class on Thursday. It says a cannon fires a cannonball at 375 meters per second at an angle of 37 degrees upward, as shown here. The cannonball splashes down in the water sometime delta t later, some distance delta x to the right. If the cannonball is fired from a height of 18 meters above the water below, what are the values of delta t and delta x? I can post a video of this one. Well, I can, so let me make one and post it. Okay, I mentioned in class several times that if you have a vector given to you, for example, this 375 meters per second, and it is not in just the x direction or just the y direction, then you can't really use it. This is not like an incline where I can tip the axes. This is a situation with this projectile. The object is moving both up, down, and left, right, but not in a straight line. So tipping the axes doesn't help me at all. I may as well leave x to mean horizontally and y to mean vertically. But the first thing I need to do is take that 375 meters per second and find out how much of it is in the x direction and how much of it is in the y direction. And again, if you're given this type of vector and you draw it out, when you draw the x and y components like this, it should make it really obvious that you have a right triangle. And in this case, the 37 degrees was given to us. That's the angle between the 375 meters per second and the x component here. The x component I can find with cosine, and if you're not familiar with how to do that by now, then you really do want to spend some time this weekend getting up on your trigonometry. Cosine 37 degrees, I put into the calculator and multiply by 375 meters per second, and I get that the initial velocity in the x direction is 299.5 meters per second. And we remember this is a projectile problem, so we know the acceleration in the x direction is 0. So it says velocity in the x direction initial, but really that doesn't change. That's the velocity in the x direction the entire time. The initial velocity in the y direction will be the opposite side of this right triangle. So it's the 375 meters per second times sine 37 degrees. And if I put that into my calculator, I get that it is 225.7 meters per second. But this is different because in the y direction, as soon as the cannonball is fired, it's experiencing gravity pulling down on it. So its upward velocity is constantly being pulled downward. It's going to eventually stop going up as it continues moving to the right the entire time. This projectile will stop going up and start coming back down. And then, as it says at the bottom of the screen here in gray, the initial question we were asked, what are the values of delta t and delta x? I can tell you right now that calculating delta t is going to be a little bit more complicated in a question like this if it's fired up at an angle and it's landing at a height other than where it was launched from. So this is sort of the worst case scenario from your perspective. If it landed at the same height that it was launched from, then it would simplify some of our equations. In the y direction, we know that the initial velocity we just found is 225.7 meters per second, and we also know that delta y is that the cannonball started at the top of the cliff and it ends at the bottom of the cliff, although far to the right somewhere. So its delta y is negative 18 meters, and I want to remind you what we talked about when we did projectiles a couple weeks back. It does not matter that the cannonball goes up and then comes back down. For the total path, whatever the entire delta t of the path is, from the very beginning to the very end of this projectile problem, delta y is negative 18 meters. We also know the acceleration in the y direction, because we're presumably on Earth. And so there's a couple ways that we could go about finding delta t. I'm going to tell you that the equation that we've used the most, which is delta y equals vy initial delta t plus 1/2 acceleration in the y direction delta t squared, works perfectly fine. But because we are starting and stopping at two different heights here, that is the one scenario where that equation would lead us into using the quadratic formula, which is perfectly fine, but I don't want to. So I'm going to show you another way to go about this without doing the quadratic. I could instead do this, which you notice does not have delta t anywhere in it, so it's not actually helping me find delta t. But it would help me find v final in the y direction. If I plug in the numbers that I know, vy initial and acceleration in the y direction and delta y, I can calculate Vy final. And remember, when I hit square root at the end, I get square root. So it gives me this value of 225.8 meters per second. But that's a plus or minus when you square root something. So you have to know this is not a Vy in the final that is positive, because the cannonball will go up and then it will come back down. And by the end of the problem, its velocity will be still to the right, but also down. So its Y velocity final is 225.8 meters per second downward. Notice that's almost exactly as the initial Y velocity was upward, and that's because the cannonball is going to go up really, really high and come back down really, really far, and that 18 meters that it actually changes over the course of the problem is relatively small compared to the entire arc. So this is pretty close to symmetrical, but not quite, so we do want to make sure that we're being thorough with this. That wasn't what I was asked for, though. So what I'm doing is I'm taking that Vy final and I'm putting it into another equation to find delta t. I know that the acceleration is defined as delta v over delta t, and delta v is v final minus v initial. So v final in the y direction minus v initial in the y direction would give me delta v. Delta v divided by a will give me delta t. So there is a way to get to the delta t using multiple steps like this without having to do the quadratic formula. Being very careful with my negatives and my subtractions and so forth, I will wind up with delta t is 46 seconds. 46 seconds is a really long time for a projectile to be in the air. So we should expect that this cannonball, if it's really going to be 46 seconds after you fire the cannon before this thing actually hits the water, we should expect that it's going to be really far away. How far away? Well, we were asked to find delta x, and we know that the velocity in the x direction was 299.5 meters per second. So it goes 299.5 meters for every one of those 46 seconds. So I would go to this equation that I've repeatedly mentioned is going to be the only equation that's useful to us in the x direction for a projectile, because all of the other kinematics equations we've talked about include acceleration, and we know that in the x direction there is no acceleration. So using this equation, I can find what delta x is, and that's the x velocity times delta t. So we get 13,798 meters, and I've got 3 exclamation points there because that seems really far. This cannon is firing a cannonball almost 14 kilometers. And so when you get your reality check, sometimes we get reality check where you step back at the end and say, like, could this possibly be true? Sometimes that could lead you astray if you're not familiar with the problem. So I'm assuming none of you have extensive time in the artillery firing off cannons. I'm going to tell you that modern cannons can definitely fire cannon shells longer than this. So you want to be careful around them. But in the meantime, that gives us our answer, 13.798 kilometers. So that's how you do a projectile problem that's a little bit more complicated like this. And as I've repeatedly said, this is the more complicated type, so I would expect you to be able to do something that is less complicated in less time. But a question like this, where it is launched at an angle and where it is not symmetrical, is perfectly fair conceptually. The only issue with it is I think it's a little lengthy for a timed assessment. Let's take a look at what the other question was that I had asked that I didn't go over in class. So this guy's trying to drag a crate. I think I gave you the numbers that I had calculated, but I didn't walk through it, so I at least want to walk through it really quickly here. We have that the mass of the crate is given as 125 kilograms, and we have that the coefficient of static friction between the crate and the floor is 0.32. And the wording of this question is a little bit odd, but really what it's asking is how hard does he have to apply this force, this F, how hard does he have to pull in order to overcome static friction? He will have to overcome whatever the maximum static friction is. And remember, the static friction equation has a less than or equals to. So we really want to find out what the maximum it possibly could be is. Static friction could be the coefficient of static friction that they did give us times the normal force, which they did not give us. So initially I might look at this problem and say, I don't really care about the normal force. It's perpendicular to the direction of motion that I'm trying to talk about. but it has a tricky way of working its way back into what we're talking about, right? In the y direction, I know the net force is ma, and I know that the acceleration in the y direction is 0 because we're only accelerating our crate in the x direction. We're accelerating it to the right. The net force in the y direction will be the normal force pointed up plus the gravitational force pointed down. So normal force pointed up minus, because pointed down, force of gravity, equals mass times acceleration, where the acceleration in the y direction was 0, so it turns our right side of that equation into 0. This, of course, means that the normal force in a question like this one is equal to the force of gravity, just in the opposite direction. So it's 125.0 kilograms times the 9.8 newtons per kilogram, and there's no other forces in the y direction to complicate it in this particular example. The normal force, therefore, comes out to 1,225 newtons, which was not what we were asked for. We just needed to plug that into the equation for static friction to determine that the maximum possible static friction in this particular problem, we found our coefficient on the previous slide to be 0.32. Therefore, the static friction has to be less than or equal to 392 newtons. The most it could possibly be is 392 newtons. So as I've mentioned in class, I won't get into like, is it 392.0 or 0.1 or whatever. And the wording of this question is a little odd for like, is the crate actually moving or not? And we're not trying to trick you with that. What we're saying is for any force that he applies up to that much, the crate does not move. Static friction is strong enough to hold it in place. And as soon as he exceeds static friction, the crate starts to move, which then takes us to the following question. If he does pull with 392 newtons, and let's assume that it's that much once the crate starts moving, the question was, okay, so now that it's moving, it's got this new coefficient of kinetic friction, how much will the acceleration of the crate be if he keeps pulling with that same amount that we just found, the 392 newtons? And it says, draw a free body diagram, of course it's given to us here, determine the net force, and use Newton's second law. So those are the steps that you'll want to use pretty much in any of our force problems. So in this problem, we'll, like I said, assume that he's pulling with that 392 newtons that we had found. So in the x direction, we'll apply Newton's second law. The net force equals mass times the acceleration in the x direction. And the acceleration in the x direction is what they asked us to find. The net force is his 392 newtons to the positive direction, minus the force of kinetic friction, because it's in the opposite direction, and that'll equal the mass 125.0 kilograms times that acceleration we're looking for. Well, I still have an unknown here in my equation. That's the force of kinetic friction. Force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. We already know the normal force from earlier, and the kinetic friction coefficient was given to us in the question, so the force of kinetic friction is the 0.15 times that normal force of 1,225 newtons. And so we get the friction is 183.75 newtons. And remember, we know that in our equation there in red, it was being subtracted because it was to the left. So the net force is the left side of this equation, 392 newtons minus 183.75 newtons. And then the right side of the equation is the rest of Newton's second law there, the mass times the acceleration. So we can then do some math and calculate the acceleration. We get 1.66 meters per second. That is the acceleration of this crate to the right. And that's it. I really hope that was helpful. Remember, you can always email me questions over the course of the weekend. I'll do the best that I can to get to them. On Tuesday, I will be monitoring the exam online. So you can take it anytime over the course of the day. It is a timed assessment, but whatever time you log in is when the timer starts for you on Tuesday. All right, that's everything.